I have become death, destroyer of worlds.
What led a mild-mannered polymath, who was more interested in philosophy than war, to utter those famous words? On a single day in 1939, Robert Oppenheimer explained how a star implodes when it runs out of fuel. Simultaneously, on that same day, John Archibald Wheeler published the first explanation of atomic fission, and Hitler invaded Poland. Today, we're going to link them all together and talk about America's Prometheus, Robert Oppenheimer, who brought nuclear fire down to a planet that was not prepared for what the atomic age would unleash.
Or become death, the destroyer of worlds. I suppose we all thought that, one way or another.
Welcome to the quantum revolution, where minds converge to reshape the fabric of reality. Among those brilliant minds, a young prodigy emerged, a man who would later become an enigma and a tragic trailblazer. This is the story of Robert Oppenheimer, as told by me, Brian Keating, an experimental physicist with a deep and abiding interest in the history of science. And what better time to take us on a deep dive into physics and filmmaking than on the occasion of the release of the wonderful film Oppenheimer by Chris Nolan. We'll be talking about the time when the secrets of the quantum realm were first unleashed upon the world and what it would mean for the future if this had never happened. Our story begins in 1922 when Oppenheimer, a prodigious Harvard graduate with a fascination and a bewilderment with the emerging field of quantum mechanics, set foot on European soil. His pursuit of the atomic secrets had taken him all the way to the University of Göttingen, where the quantum revolution was in full swing. Under the guidance of his advisor, the Titanic Max Born, Oppenheimer learned the rules of the atom and how those rules would reshape the planet. And he began the journey into the enigmatic world of the subatomic particle. The peaceful interwar years were good to him. He blossomed, and after returning to the United States in 1928, Oppenheimer's academic career blossomed. He joined the faculty of the University of California at Berkeley, rapidly gaining recognition for his brilliance. His eclectic interest ranged from astrophysics to nuclear physics, spectroscopy to quantum field theory. Collaborating with his young, brilliant student Hartland Snyder, he envisioned a cosmic phenomenon that would play a role many decades later in Christopher Nolan's other great physics-based film, Interstellar. The genius duo developed mathematical models that described how, when a massive star exhausts its nuclear fuel, the inward pull of gravity becomes overwhelming, causing the star to collapse in on itself, resulting in an incredibly dense region of space where gravity is so strong that nothing, not even light, can escape its crushing grasp. You guessed it, a black hole. The idea was so wild it even offended Einstein's delicate sensibilities. Oppenheimer built Berkeley's program in theoretical physics to be one of the best in the world, and he became known as the founder of the American School of Theoretical Physics. Although he had a reputation for being arrogant, he was a patient and beloved mentor, and he garnered the respect and admiration of his students and colleagues, allowing him to leverage their talents as well as his. Oppenheimer could selfishly have stayed focused on theoretical physics and academia, but fate intervened. As the world plunged into darkness with the outbreak of World War II, Oppenheimer's scientific expertise was sought after to confront an unprecedented threat: the rise of Nazi Germany and their potential to harness the power of the nucleus for destruction weighed heavily on the minds of many a physicist. As the war raged in Europe, the world divided. Many of Oppenheimer's former colleagues from Europe were caught up in the turmoil. Loyalties were tested. Jews were persecuted. And many of Europe's great Jewish scientists fled the continent, either to England or to the United States, including Einstein, Born, Leo Szilard, Edward Teller, John von Neumann, and Enrico Fermi. Troublingly, some physicists remained loyal to the Axis powers in the German fascist state, including the quantum theorist Werner Heisenberg. It became clear to many scientists that based on quantum theory and discoveries in nuclear physics, that atoms could be split, and a new and extremely powerful weapon could be built. If the Allies could harness the atom, though, so could Nazi Germany. Some, like Edward Teller, foresaw the creation of an even more powerful weapon, a super bomb based on nuclear fusion, using a fission reaction to trigger the necessary energy conditions. But that's a film review for another day. Refugee physicists knew firsthand the consequences of Nazi aggression and were the first to become alerted to the terrifying prospects of Nazi Germany building a super weapon first. In August of 1939, they persuaded Albert Einstein to alert President Franklin Roosevelt of the threat in a famous letter that grimly warned, "It may soon become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain this could be achieved in the immediate future, and extremely powerful bombs of a new type may thus be constructed." These words persuaded President Roosevelt. In less than 2 years, the entire planet, though, would be engulfed in a world war. Later, on December 7, 1941, the United States was drawn in to the conflict, owing to the fact that attacks on Pearl Harbor by Japan, and the US was almost alone in fighting a two-front war, in Europe against Nazi Germany and in the Pacific against imperialist Japan. America had to make the bomb first in order to end the war.
Before the Nazis do.
Oh my God.
Scientists were assembled and committees were formed, and a race to build the atomic bomb had begun. In the New Mexico desert, a city-sized compound emerged.
A place called Project Y. It was Los Alamos, but all that anybody knew was Project Y.
Los Alamos. It housed the brightest scientific minds in the world, including the very famous Richard Feynman, who recounts his exploits there in many of his popular physics books. They worked tirelessly to construct the first atomic bomb. Oppenheimer, you might guess, would be an unlikely choice to lead this project, but he proved to be a charismatic and relentless organizer. He built a team of extraordinary individuals, pushing the boundaries of what was thought possible. Working alongside him was an officer in the Army Corps of Engineers, Leslie Groves, who had just completed his duties supervising the construction of the world's largest building, the Pentagon. Groves was ready for a wartime assignment overseas, but instead he was tasked with the monumental feat of creating the Manhattan Project. Groves knew he needed to recruit the best scientists in the country, and he got what was considered to be an unusual choice for a partner, the elite Berkeley professor Robert Oppenheimer, with no administrative or military experience.
He's a general. I've got all the soldier I need.
The duo formed a brilliant pair. Oppenheimer quickly grasped the importance of the project, and he helped to inform Groves of who would be the greatest scientists to recruit. He scooped them from academia and industry. Few could resist his charisma, his quiet confidence. He transformed himself into a bookish theoretical physicist, into an organizer, a confident leader, and a relentless recruiter. By April 1942, Oppenheimer and Groves had constructed an entire city-sized compound in Los Alamos,
Build him a town.
dedicated to the construction of the atomic bomb. Over 8,000 physicists, chemists, metallurgists, engineers, staff, military personnel, security, and family members occupied a top-secret facility during the war. A single post office box, famously known as P.O. Box 1663, serviced over 300 buildings. At Los Alamos, the nation's best and brightest in physics worked together under enormous stress to build the first atomic bomb. But how did it work? A few months after the initiation of the project, Enrico Fermi produced the very first chain reaction, a process undergoing sustained nuclear fission. It was understood then and there that a superbomb could be made and detonated. But what is nuclear fission? The key process that enabled the atomic bomb and today enables nuclear power. Fission occurs when there's enough energy to shatter apart a nucleus. When the shattering takes place, the fragments that emerge, have less mass energy than the original parent particle had. This process cannot be triggered by an ordinary proton or an electron because they, like the nucleus itself, are charged. No, instead, to sneak through the Coulomb defenses, the electrostatic repulsion of the positively charged nucleus, that requires a very special actor indeed, the neutron. The neutron, which you last saw on this channel in the video entitled Neutrons Die in 15 Minutes, is an unstable particle that comprises the innermost sanctum of the nucleus, but they can also be used in isolation to dislodge and fragment a heavier, more ponderous nuclear parent particle. And there is a deficit, and that deficit in energy between the parent nucleus and the daughter nuclei that come out is converted to pure gamma ray energy, heat. And that heat is what causes either the destructive force of an atomic bomb or the slow heating process used to boil water in a steam turbine when used for peaceful purposes in a fission reactor. Sustainable nuclear fission is only achievable under special conditions. Neutrons must be prepared, and they must be beamed to hit the nucleus with enough energy and frequently enough such that they induce a reaction that in turn release more high energy particles that can bombard more nuclei, and so on, and so on, and so on. A chain reaction.
Good. I know how a nuclear reactor works.
Some elements have properties that can sustain such a nuclear reaction. These fissile elements have a large enough neutron multiplication factor, in other words, how many neutrons are produced in each time the parent nucleus gets bombarded by an incident neutron, that they can produce a sustained chain reaction. This occurred in 1942 by Enrico Fermi and his team at the University of Chicago underneath their football field. Uranium is one such prospective fissile material ingredient. As we've explained in other videos, elements can have different numbers of neutrons in their nucleus, forming what are called isotopes. The same number of protons and electrons, but different numbers of neutrons and different atomic weights. But only the uranium-235 isotope has the elusive neutron multiplication property useful to make it into fissible material. But uranium-235 only makes up 1% of the naturally occurring uranium.
1, because that's the lowest number.
Separating it from the more profligate, the more numerous 238 isotope is one of the greatest challenges of the Manhattan Project. To obtain just a few kilograms of the purified uranium-235 required the construction of a massive industrial-scale processing facility at Oak Ridge, Tennessee, employing 75,000 people at its peak. One of our famous UCSD professors, Harold Urey, the namesake of UCSD's Urey Hall, our chemistry department, developed one of the techniques used to enrich the uranium from uranium-238 to uranium-235. This process that he developed is called gaseous diffusion.
You know isotopes.
64 kilograms of enriched uranium was constructed at Oak Ridge and ultimately used in the first atom bomb dropped on Hiroshima. But it was early realized by the brilliant scientists of the Manhattan Project they couldn't make enough uranium-235. This was a key, gripping plot point, as you may have noticed in the movie as well. A second element proved to be fissile as well, plutonium-239, which could be created from uranium-238, but it's one atomic unit heavier, so it must capture an extra neutron. That's called a breeder reactor. Many questions needed to be answered. Could a chain reaction be controlled enough to achieve detonation? How much fissile material would be just right to achieve critical mass? Could a bomb be made that was small and light enough to be delivered on an airplane? How much force was needed to be exerted to achieve a chain reaction in a bomb design? What would be the radioactive side effects? Would there be dangers to the crew dropping the bomb? And what about a fusion superbomb? How could that be built? Weighing on the scientists working on the Manhattan Project were the moral and ethical questions of creating and deploying a weapon with the potential to engulf the entire planet in nuclear fire. To produce the precious plutonium-239, another massive complex was constructed in Hanford, Washington. It was used to create the very first atomic bomb ever detonated in the Trinity test. Trinity used an implosion design. This was the second nuclear weapon and the last to be used, as we'll see. It required a mere 6.2 kilograms. Such was its advanced destructive power over the uranium bomb. Oppenheimer and Groves relentlessly drove their teams to produce two different designs, overcoming seemingly endless theoretical and practical obstacles. Weighing in the background was always the concern of secrecy and security, for the fear was the Nazis or the Japanese would get this device first and perhaps steal it from the scientists themselves or their family members. Trinity shook the world. As the first atomic bomb exploded, its mushroom cloud became a harbinger of the immense power unleashed. Scientists were overwhelmed with emotion, and Oppenheimer quoted those famous words I uttered at the very beginning of this video. "I have become death, the destroyer of worlds," from the Bhagavad Gita. While the development of Trinity and the atomic bombs came too late to end the war in Europe, Germany had surrendered 2 months earlier, the war in the Pacific was still raging. But by now, Japan's fate was sealed. To rapidly end the war in the Pacific, preventing horrific casualties on both sides, estimated to be up to 1 million American and Japanese soldiers and civilians, President Harry Truman made the order to develop and drop 2 bombs on Japan. Only the newly designed and specially modified B-29 Flying Fortresses were capable of delivering these giant bombs. After extensive planning and training, a small team of scientists from Los Alamos volunteered to be deployed at great risk to themselves and assemble the bombs on the small South Pacific island of Tinian to support the 509th Group of B-29s commanded by Paul Tibbets. On August 6, 1945, the United States detonated an atomic bomb over the Japanese city of Hiroshima. Three days later, a second bomb was dropped on Nagasaki. The aerial bombings killed between 129,000 and 226,000 people, most of whom were civilians. The Japanese would not end the war for another 3 weeks, but the legacy of the atomic bomb persisted. Oppenheimer, the father of the atomic bomb, was initially hailed and praised as the most famous scientist and a hero, but his conscience always wrestled with him. What were the ethical implications of nuclear weapons? In the immediate aftermath of World War II, the Cold War unfolded. Suspicions and accusations marred many scientists' reputations, including Oppenheimer's as well. Oppenheimer was always circumspect about the use of nuclear weapons.
Science has profoundly altered the conditions of man's life, both materially and in ways of the spirit as well.
Along with colleagues warning about the moral implication of using atomic bombs, many warned of the spread of nuclear weapons, in particular to the enemy of the Cold War, the Soviet Union. Oppenheimer never apologized for the use of atomic weapons in World War II, but he did argue for international controls. After the war, Oppenheimer accepted a position as the director of the Institute for Advanced Studies, joining Albert Einstein and Freeman Dyson, my very first guest on Into the Impossible podcast. A shadow of doubt was cast over Oppenheimer's loyalties, and he was ceaselessly investigated and surveilled by the FBI and the deep state. As the Cold War commenced and the Soviet Union got the bomb, there came the Red Scare, McCarthyism, and the House Un-American Activities Committee hearings. Oppenheimer's loyalty and reputation were attacked.
There's no proof there was a spy at Los Alamos.
But he stood his ground and continued to serve in many government advisory roles requiring a security clearance. But in 1954, a grueling and controversial 4-week security hearing led to him being stripped of his security clearances and his role in government ceased. He remained justifiably bitter about this assault on his liberties and reputation for the rest of his life. Yet, in April 1962, the US government made partial amends for the treatment Oppenheimer suffered during the McCarthy years. President John F. Kennedy invited him to the White House, and in 1963, President Lyndon Johnson awarded Oppenheimer the highest honor given by the Atomic Energy Committee, known as the Fermi Award. Oppenheimer died of throat cancer just 4 years later, February 18th, 1967. Today, the legacy of Robert Oppenheimer and the Manhattan Project endures. Calling for a Manhattan Project level of effort is synonymous with getting the best and brightest on board to tackle the greatest imaginable challenges. The risk of nuclear war is greater than ever, with 9 countries possessing over 13,000 nuclear weapons. The promise of nuclear energy has been sullied by the problems of radioactive waste and proliferation, despite it being one of the most promising, if not the most promising, solution to global climate change. the pursuit of understanding the nature of reality through quantum mechanics endures. The insights gleaned by Oppenheimer and colleagues during the Manhattan Project provided a foundation for a new generation of physicists to understand the nature of reality through quantum mechanics. And new branches of theoretical physics are coming online at ever-accelerating rates. With great power comes great responsibility. Harnessing the atom led to humanity's ushering in of the atomic age, of nuclear energy, but also of nuclear proliferation. We today live under the threat constantly of hair-trigger nuclear warheads, and we must remain guided by wisdom and compassion, not unlike that of J. Robert Oppenheimer. Oppenheimer's story is a tale of brilliance, ambition, responsibility, power, but also betrayal and regret. Oppenheimer's colleague John Wheeler once quipped, "We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shoreline of our ignorance." So, as we navigate the uncharted waters of the quantum and unravel the secrets of the universe, may we, like Oppenheimer, strive to use this knowledge for the betterment of humankind, the banishment of ignorance, and the preservation of our fragile, tender planet. Nolan's film is out now, and it is spectacular. Get a ticket. It's not very often you get to see a film where the main star is a physicist. And join us on our next cosmic voyage as we dive deeper into the wonders of the cosmos and the infinite frontiers of human knowledge and imagination. Until then, remember, always be curious. If you enjoyed this video, please click here for a playlist curated just for you about experimental physics and cosmology.